Good afternoon, everyone, and welcome to RGI's Best Practice webinar on Grid Practices Advancing Renewables-based Electrification. We're very happy that you're all joining us today for this very interesting webinar, as I find. We have great speakers for you. But before we get into that, a little bit of housekeeping. So my name is Bätjer. I'll be your moderator today. For you to know that this webinar is being recorded and afterwards will appear on our RGI website and on our YouTube channel. For a good experience together, we ask you to keep your camera on if possible, so that we actually feel like we're in a room together and are having an exchange. But unless you're speaking, please keep your microphone off. For us to know who's with us, it would be great if we not just saw your name, but also the organization that you represent here today. So if you know how to do that, please rename yourself so that the name that shows in the little window that also shows your video represents your name and your organization. And if you do have any question, which we hope that there will be lots during the course of this webinar, you can either post them in the chat, or preferably you can use the reactions field and then raise your hand and ask your question directly to us or our experts that we have with us today. Next slide, exactly. So just very quickly, for the people who might be new to RGI, we are an association based in Berlin with quite a unique membership structure, as I find. It's the unlikely combination of TSOs and NGOs who have decided to work together on the energy system of the future under the roof of RGI. One of the big things that we do as RGI is we collect best practices from all these members that you've just seen on the previous slides and beyond. And we do this mostly via our RGI Grid Awards, but we always try to share those best practices in and across many different channels to reach as many members of our potential audience as possible. So this work includes best practice reports, showcases in our best practice database, presentations at our regular best practice fairs, and our dedicated best practice corner in our newsletter, in which we also promote events such as today's best practice webinar. So if you're interested to learn more about any of these things, we of course invite you to sign up for it. And then of course I didn't mean to go forward to the next slide. Let's stay here. Another good practice sharing approach is talking about the practices that we're aware of during webinars such as the one today. In our best practice webinars, we always share some of the most laudable approaches that we've recently come across, with the goal of disseminating and inspiring those who hear about it, and specifically also to give you, the audience, the opportunity to ask lots of questions so you can deepen your understanding as much as possible. So I hope that you all came with many questions, or will develop many questions in the course of this webinar once we heard today's presentations. Yeah, and speaking of today's topic, today we're going to talk about grid practices that advance renewables-based electrification. Of course, this can encompass quite a lot of different practices, but today we want to specifically focus on grid operating practices. Operating practices that enhance renewables integration and reduce curtailment, as well as the need for deployment of new grids. And thus make a big contribution to bringing us closer to a transformed energy system. We often hear how difficult it is and how many challenges still lie ahead of us in getting the grid ready for a largely renewables-based energy system. So I'm extremely happy that today we will hear from grid operators who are doing some of the heavy lifting in working on the solutions that we need, and who are already applying them in their daily operations. And the first of our presenters is Fagen from EirGrid, who will share the Irish grid operators approach of increasing the rate of change of frequency limit to ±1 hertz per second. And then we have Dr. Marcel Ludwig from Amprion, who will talk about the coordinated reactive power exchange that German TSO Amprion, that Marcel represents here today, has embarked on with the biggest TSO in Amprion's control area in the west of Germany. I hope that you're all as excited as I am to hear more from both of them and ask questions, for which you will have time after you have heard from both of our speakers. Directly after the presentation, we ask you to only ask comprehension questions that clarify aspects you might not be sure about from the presentations you've just heard. And then questions that go beyond this, please save until the end when we'll have a big Q&A section in this webinar. We officially have this webinar scheduled. Oh, and I see there's a typo here. So this is supposed to say until 14:45. So we're officially scheduled to go until 3 p.m. today. But if there's a lot of questions, we're prepared to stay a little bit longer and answer anything you might want to know. Good. I think this is enough out of me. So without further ado, let's get started. And yeah, Emma, the floor is yours.
Great. Thank you so much, Stephanie, for the introduction and the welcome. And thank you so much to RGI for all the work that you do and for inviting us here today to share our knowledge and our good practice. And we were thrilled to win the award at the end of last year in the innovation and in the system integration category. So we're delighted again to share the history of this project with everybody here today. So thanks so much, everyone, for joining. My name is Emma Fagen. I'm the DS3 Program Manager in EirGrid. EirGrid is the TSO in Ireland, and SONI is the TSO in Northern Ireland. So this was a joint project with both of these TSOs. So just to give a little bit of background, over a decade ago, ambitious targets of 40% of electricity to originate from renewable generation by 2020 were set. They seem quite small at this stage, where given what we know now, but back at the end of the 2000s, this was very, very ambitious. We did acknowledge that wind generation would make up the majority of this. And we set about doing some really technical, detailed studies with the help of some partners. So we published the Facilitation of Renewables study in 2010, and this identified that wind generation levels up to 75% instantaneously would be possible on the island of Ireland, but with a lot of mitigations and a lot of work to do to get to that point. One of the limiting factors was that the RoCoF, that's rate of change of frequency, which we'll go into in a minute, but that the existing level at the time of 0.5 hertz per second would be a limiting factor. So this was a key item that we needed to consider. Just to have a quick look, first of all, at the transmission system on the island of Ireland. So as I mentioned, EirGrid is the operator for Ireland, and SONI is the TSO for Northern Ireland. We have high voltage network of 400, 275, 220 and 110 kV. We have an all-island peak demand of around 7 gigawatts. Our minimum demand is about 2.5 gigawatts. We have about 6 gigawatts of installed wind generation on the island. And in December 2023, we had our peak level of wind, which was 4.65 gigawatts, which was quite an achievement. We do have 2 interconnectors from Northern Ireland across to Scotland. There we have the Moyle LCC HVDC interconnector, that's 500 megawatts, and then from north of Dublin we have the east-west interconnector, and that's also the same size, but it's VSC technology. And there's 2 more under construction at the moment, and the Green Link across to Great Britain as well, and then the Celtic interconnector from Cork in the south of Ireland over to Brittany in France. So exciting times there as well. So that's just a little bit of background. We are a synchronous area. We share the same system frequency. We do have a double circuit tie line between Ireland and Northern Ireland there, and that's 275 kV. So moving on then to the RoCoF in terms of a little bit of background on that. So as you know, the system frequency is set to 50 hertz, and when there's disturbances in the system, frequency will change. So if we lose a generator, frequency can fall, and if we lose demand, frequency can rise. And it's the rate of change of this change of frequency that we refer to as RoCoF or as COF. And prospective RoCoFs in the system after a disturbance are calculated in real time in our control rooms. And this is a calculation which is based on the online inertia and the size of the maximum in-feed or out-feed. And we monitor this value all the time in our control rooms to ensure adherence to the operational limit. So we're constantly considering contingencies that might lead to a frequency change, and we would consider what the RoCoF would be as part of that. Higher levels of renewables, then replacing conventional synchronous generation, that leads to reduced system inertia and therefore increased potential RoCoFs in the case of a disturbance. So this is why we need to ensure that the RoCoF levels are higher so that we can allow that additional renewable generation on in place of the synchronous generation. Every device on the system has its own RoCoF setting, and if that setting is breached, that device might trip in sympathy, and therefore you'd actually propagate that disturbance. So this would lead to a system stability risk, which we don't want. So what did we do? We set out a program of work called the DS3 program. So DS3 stands for delivering a secure, sustainable power system. And we focused on 3 areas: system policies, system tools, and system performance. So RoCoF kind of fell under the top 2 there in terms of we had our own policy, and in terms of the system performance, what RoCoF levels could the system handle. So this DS3 program had its own advisory council, which was made up of industry and academia. So we met with them 3 or 4 times a year for over a decade, got their feedback on our proposals and where we were going next. In addition to the DS3 Advisory Council, a working group was set up under the auspices of the Joint Grid Code Review Panel, both in Ireland and Northern Ireland. And this group set about to look at various different aspects of RoCoF, what we would need. We were looking at how we would get from the 0.5 hertz to something higher. Would 1 hertz be enough, etc. And a huge amount of technical specialists were brought in to carry out system studies, both in-house and external. We had a lot of interaction with various different stakeholders, the distribution system operators, the regulators, government departments, etc., and bilateral discussions with the generators, etc. So RoCoF was just one part of this wider program, but it was a really crucial part of it. The Joint Grid Code Review Panel also looked at alternatives to the RoCoF program. However, these were deemed not suitable, and that the RoCoF increase would need to go ahead. One massive part of the project then was after the regulators agreed with the Grid Code proposed change from 0.5 hertz to 1 hertz per second. That was back in 2014, but it was subject to a generator implementation project going ahead, and it really been proven that the higher levels of RoCoF could be implemented by the industry. So this program involved categorization of the generators in terms of their importance to contribute to being able to ride through the RoCoF higher levels. A massive amount of studies were needed to be carried out by the generators and checked through by EirGrid and the regulators, etc. So this went on for a number of years then before we were in a position to do some compliance testing. So the exact nature and the scope of the studies was quite varied. They incorporated electrical dynamic simulations to assist us in assessing the impact on the system, and mechanical and plant integrity studies as well to examine whether the safety or plant integrity issues that were under consideration would materialize or not. So again, huge thanks to the conventional generators who put the effort in to get their plant studied, tested, and up to 1 Hertz per second. Furthermore, there was a lot of work done with the distribution system operators. Just some reflections from we've two DSOs in Ireland, not many compared to other countries in Europe. So we have one in Ireland and one in Northern Ireland. One of the main impacts in Ireland was that a typical setting, a RoCoF setting of 0.4 Hertz per second, was used for anti-islanding interface protection on pretty much all distribution connected generators in Ireland. And the vast amount of those relays were on the customer side. So over 800 sites had to have their settings changed. And this was a massive undertaking by the DSO. It happened over multiple years, and amazing achievement that we got everything up to, with the exception of just only a small amount of megawatts left of legacy generation, and that had their settings successfully changed. In Northern Ireland, similar but slightly different challenges. Again, in Northern Ireland, a lot of the renewables is embedded on the distribution network. The tight timelines were a challenge as well. The completion of the RoCoF loss of mains Strathclyde studies to verify that the DSO could desensitize the RoCoF settings whilst maintaining the risk of islanding at an acceptable level was required, and it required huge resources on their side and a lot of system data as well. And just with the limited control that the system operators had was a challenge as well. So also keeping the generators informed as to the logic and the reasoning behind why we were doing this was also really important. So again, thanks a million to everyone at the DSO side for all of the work that was done there. So then once we had all the settings updated and we were confident that the large thermal plant could were compliant with the 1 Hertz per second, we set about our operational trial. So we're already nearly a decade into this project at this stage. We carried out any kind of change to our operational policy is quite rigid, and we have to follow quite a detailed process. So we carried out pre-trial studies, and then these informed our internal governance teams as to the safety and security of going ahead with this trial. One enabler for the trial was the advent of one of our new tools. This is the LSAT tool, Look Ahead Security Assessment Tool. This is a really incredible tool that it provides a real-time and a look-ahead assessment of the transient frequency and voltage stability of the system. And it allows grid controllers to take appropriate actions if necessary. So this is operating every 5 minutes in our control room, and it's providing that look-ahead facility to the control room operators, so they can see if a potential RoCoF violation is about to come along, and they can take the necessary mitigations ahead of that. So then we kicked off the trial in 2020. The pandemic slowed things down a little bit, but we got going after a few false starts. And during the trial, of course, we did a lot of in-trial analysis, making sure at the various checkpoints that things were working well. In parallel, we also increased our system non-synchronous penetration levels. So at the start of the trial, these were at 65%, and we did 2 parallel trials to get our non-synchronous generation levels up to 70 and then 75%. So wouldn't have been possible to get up to the 75% without this, the higher RoCoF levels being enabled. Towards the end of the trial, then we took a data freeze and we did our end of trial analysis. So this involved a huge amount of studies and frequency stability stimulation. So we took 8760 snapshots from the previous year of the trial, updated some models, and we investigated the severity and frequency of either frequency nadir and zenith, or RoCoF levels beyond 1 Hertz per second, the insecurities there. We then identified what was causing those, looked for mitigations for them. There was only a very small amount, less than 100 issues that needed to be considered there. So following all those mitigations, we were then happy to complete the trial and announce our new operational policy of 1 Hertz per second. Ongoing monitoring and compliance, again, really important to keep an eye on that. So just to show you how things have changed. So again, SNSP stands for system non-synchronous penetration. So this is the level of renewables. There's a calculation there with interconnectors and demand as well. But you can see how in 2023, we operated for 40% of the year with the SNSP of 50% or higher. So these new operational policies and changes are really making a difference. Just to quickly then move on to the future, where do we go now? So 2030 has brought some new targets for us, and we are looking to go up to 80% RESI by 2030. That's double the 2020 target. And a lot of challenges to go alongside that. We have a new program of work. DS3 has been replaced with our SOEF, Shaping Our Electricity Future Roadmap. And we have 4 work streams: networks, engagement, operations, and markets. And our aim is to get our non-synchronous penetration level up to 95% here. This is the only way we think that we can hit the 80% annual target. And we have an operational policy roadmap that sits alongside the program. And this is just one snippet here from our dynamic stability roadmap. The last item there might be of interest: the minimum number of units. So currently on the island of Ireland, we have a rule that we must always have 8 conventional units dispatched on. So at the moment, we're trialing bringing that down to 7. And the trial is going really well. We hope to complete that in the next few months. And obviously, by reducing those synchronous units requirements, we can make space for more renewables. So this is really key to that. We're aiming to get down to 3 minimum units by 2030, which will be a challenge, of course. So that's the end of my slides there, and hope you found that little history lesson of our RoCoF project interesting, and happy to take any clarification issues right now, and then we'll have a deeper discussion after the next presentation.
Great, thank you so much, Emma. Extremely interesting. As Emma said, we have time now for clarification questions. Are there any from our audience? Yeah, thanks, Esther. So my colleague has just posted a link to more information on this interesting project by EirGrid and SONI. So if you do have any immediate questions, please raise your hand. I'm not seeing anything. So yeah, if there's clarification needed later on, you can also still ask that during the big... there is one in the chat. Okay. Thanks so much, Emma, says Anne-Marie McCaig. Will 1 hertz per second be sufficient for 95% SNSP?
Great question, Anne-Marie. Nice to hear from you. So we do believe that the 1 hertz per second is sufficient to meet the 2030 targets. So as you can see here in our roadmap, the RoCoF there is staying the same at 1 hertz per second out to 2030. But you know, EU network codes are coming, potentially requiring plant to have a higher RoCoF level. So maybe as the decades continue on and all plant is up to that new level, we might be able to avail of that. But for the moment, we're happy with the 1 hertz per second.
Mm-hmm. Great. Thank you so much. And then we have a second question from Declan O'Hara. How much in conventional generation inertia has been replaced by synchronous condensers?
So at the moment, there is a 4,000 megawatt second synchronous condenser in the southwest of Ireland. We are having a procurement at the moment to procure some additional sites. So I think it's up to 10,000 megawatt seconds are being procured in this round. And it'll depend on where the successful applicants come from. Yeah, so our current inertia floor is 23,000 megawatt seconds, and that is made up of conventional generation and the synchronous condensers as well.
Great, thank you so much. Good, then we'll close the comprehension question session here, and I would like to give the floor to Marcel Ludwig to talk about their reactive power exchange practice. Marcel, the floor is yours.
Can you see my screen?
Yes, you can. Looks
okay.
great.
Thank you for your introduction, Stephanie. My name is Marcel Ludwig, and I'm working for Amprion. Amprion is a transmission system operator, and here I'm working in the asset management in the Department of Grid Stability. And today I want to talk about the coordinated reactive power exchange between electrical transmission and distribution grid. One short information, One short information about Amprion. Amprion is one of the 4 transmission system operators in Germany, in the west of Germany, and we operate an 11,000 kilometer long high voltage grid in Germany, and we supply up to 29 million people with electrical energy. For your information, this is more than 1/3 of the German citizens. And we are responsible for the coordination of power flows in Germany and also for Northern Europe. And in Germany, we have a lot of challenges depending on our German energy transition. Here you can see some different maps from 2015. Here you see some surpluses and deficits of electrical energy in Germany. And in the right picture, you can see a prediction of the surpluses and deficits. And for 2030, we think we have surpluses of energy in the north of Germany. This is, of course, of the expansion of renewable energies, for example, onshore and offshore wind parks. And we have in the south of Germany a decommissioning of conventional power plants. Here, coal and nuclear power plants. For your information, last year in April, the last nuclear power plant was shut down in Germany. And so we have a surplus in the north of Germany and a deficit of energy in the south. And therefore, we have higher transits from north to south. With this higher transits, we have higher efforts for voltage control in our grid. And voltage control is made by reactive power control. And with reactive power control, we can lift the grid voltage and also reduce the voltage in our grid. And therefore, we have a high need of reactive power in our grid. But of course, of the decommissioning of conventional power plants, we have a missing provision of reactive power. And therefore, we need new resources, reactive power. There are two possible solutions. On the one hand, we can use own compensation assets. And on the other hand, we can use existing reactive power potential from the distribution grid, from solar and also from wind parks. And this was the idea for our project. On this slide, you can see a pyramid of the grid levels. And you will see we have the transmission grid, 380 kilovolt, with offshore wind parks. Then we have the high voltage grid, 110 kilovolt with onshore wind parks, the medium voltage grid with big solar parks and also smaller wind parks. And then we have the voltage grid, low voltage grid for households. There we have some solar, photovoltaic or solar units, which are situated on the roof of our household. What you could see is that the most of the reactive power potential is situated in the distribution grid. But there is a little problem because the potentials are not there's no communication technology, and therefore it's not available to use this. And if there would be a communication This is very complex because millions of households have to control it. But we think in the high voltage and also in the medium voltage, there are big potentials of reactive power to control. So now let's talk about the story and the experimental procedure. We have on the right here in the purple box, we have the transmission grid, 380 kilovolt. This is a transmission system operator Amprion as company A. And in the old times, we had conventional power plants which provide reactive power. But now we have the decommission of nuclear and also coal power plants. There's no provision of reactive power by conventional power plants. And now we need new sources for reactive power. And therefore, we make a request to the distribution system operator, because we have a huge expansion of wind power plants in the distribution grids, and there new grid customers are situated. And now what we do, we make a request of reactive power to the distribution system operator, and the distribution system operator make a request of adjustment of the operation point to the wind power plants. And the wind power plants select a new set point and can provide the distribution system operator reactive power. And this reactive power is forwarded to the transmission system operator. This is the whole magic, and the whole magic is situated at the transformer between the interface between the transmission grid and the distribution grid. Maybe you will think this is quite simple, but in Germany we have the concept of unbundling. We have a company for transmission system operation, then we have a company for distribution system operation, also the grid customers. They are totally different and independent companies. There's no interaction. They have different business objectives and also different operation objectives. And therefore, it's very complex to make a communication between these companies. Yes, here you can see the field test measurement. I will show here, I show you the reactive power control at the transformer. Let's look back. Here you can see the transformer between the distribution system grid and also the transmission grid. And this is a measurement at the transformer. Now what you can see is in the first blue box, we have a reactive power request for lifting the voltage. This is the first blue box. And in the second blue box, we have a reactive power request for reducing the voltage. This was a real measurement. And now I can show you the measurements for voltages of the transmission grid, 380 kilovolt. This is our grid. And also the measurement in purple for the distribution grid. This is a 110 kilovolt grid. And what you see, we can adjust the voltage. We can lift the voltage up to 500 volt and also reduce the voltage up to 500 volt. After we have made the field test, we think about activation concepts. And here you see the activation concept, one activation concept, but with different levels of automation. In the first level of automation, you see the transmission system operator, Amprion, make a telephone call to the distribution system operator. And the distribution system operator control manually the wind power plants and solar plants. And in the second level of automation, the event is recognized automatically, and the request for lifting or reducing the voltage is sent by an automatic message. And on the highest level of automation, we have the possibility of an optimization engine, which calculates the best reactive power demand or request. And here you can see the message is sent automatically, and we have, and the TSO has a smart grid with an automated control of its renewable energy resources. This is one concept, but it has a high flexibility and scalability because depending on the technology of our distribution system operator, we have many distribution system operators, we can select between this level of optimization and therefore we have a high flexibility to decide which concept we use. Okay, let's talk about the results and benefits of the project. We have tested in a real field test the coordinated reactive power exchange, and between our with our distribution system operator, we have an agreed activation concept. And we think we have a high scalability because the concept for coordinated reactive power exchange can be used in every electrical grid in the world. Maybe some TSOs and DSO do this. And we think we have a high influence, especially in Germany, because Amprion and the distribution system operator E.ON are the two biggest grid operators in Germany. Therefore, we think we have a high influence to, in Germany. And actually, we use this concept in our daily business. And yes, and last year, I think up to 20 times we have this activation concept used. And now the final and the major point is that we become more and more independent from conventional energy resources by using the available reactive power potentials from wind power plants and maybe from solar power plants. And so we are no longer dependent on the reactive power of conventional power plants. Now, finally, I thank you for your attention, and now I'm glad to hear your questions.
Thank you so much, Marcel. Extremely interesting to get deeper insight into this practice as well. Do we have any questions from our audience as to how this practice works? Any comprehension issues? I'm going to wait just a little bit because last time it also took a little while for people to type their questions into the chat. So I'm going to give you a bit more time, but also if you want to be quicker, just raise your hand and ask your question directly. We have one, two. Okay, we're going to start with Riccardo Vailati from Arera in Italy. So he says, dear Marcel, did you maybe prepare a technical/scientific paper describing the reactive control practice? So I gather he wants more information. So can you find more detailed insights into this practice somewhere?
Yes, in the scientific way, we have at the universities a lot of papers about the reactive power exchange, but in this context, we want to show the real world, and so there is a German paper to this issue, but not an international, international paper.
Do you have any plans of maybe translating that? I think that could be interesting for an international community as well. You don't need to answer this
maybe.
now, but maybe just as a food for thought. Good. Then we have a question from Michael Hogan from the Regulatory Assistance Project. He's asking, how independent does this practice make you from conventional resources, that is? So it seems like we're going a bit into the open discussion already with these questions, which is fine. So I will now open the floor then for broader questions, not just comprehension questions. And maybe we can spotlight Emma then as well, and will be a little panel here. And so if you have any overall questions that maybe also connect between the two practices, feel free to ask them now. But we'll start with Mike's question.
Should I answer? No?
Yes, please.
Okay. The question is more than that we have to be independent from conventional power plants, because our federal government plans to reduce the conventional power plants. Only gas power plants will be situated or installed in the future. So we have to be independent from conventional power plants in the future.
Yeah, I guess the question is, and correct me if I'm wrong, Mike, but like, how far along are you in this process? How independent are you already now?
Okay, actually we built a lot of compensation units. So we think that this actually it's a small, maybe a middle provision possible, but actually we are not completely independent from conventional power plants. But we hope maybe 2030 it's possible to be completely independent.
Okay, that sounds like a good ambitious plan. Okay, we have another question. Declan is asking a question again. We've heard from him earlier. Is there any fear regarding cybersecurity with this automatic control, especially with the global conflicts arising? How is Amprion trying to avoid these risks?
Yeah, there we have a big sensibility, and therefore, actually, we use only the telephone way. But in the future, we want to use.
So, in terms of the automation that you talked about earlier, you're in the phase 1 column, right?
Yeah, but in the higher automation level, you're right. We want to make. We have some concepts for this, but our grid operators have to accept the request. There's always a human checking the request to avoid some cybersecurity problems.
Thanks. We have a lot of questions for Marcel right now, but I maybe jump a few and ask Emma first, and then I come back to Marcel. So, Ruari Mac Ilhatton, I'm so very sorry for butchering your name, is saying, hi, Emma. You mentioned how the RoCoF change will be beneficial in reducing the MUON. Do you also anticipate it will decrease the need for synthetic inertia / SIR? Sorry.
Thanks for the question, Rory. So yes, absolutely, it's needed to reduce the minimum number of units as we go on. In terms of synthetic inertia, I'm not 100% sure on that. We will be looking at the inertia floor levels and seeing what we are requiring there. So currently, as I said, it's 23,000 megawatt seconds, and we are required under the SOGL to reassess that level every 4 years or so. So as we will be looking to reduce that inertia floor level And that then may have an impact on the SIR for sure.
Thanks a lot. Then we have a question from Thomas Schaub. Not sure which organization he represents. What is the effect of the reactive power on the 110 kV level? This is for Marcel.
Yes, there are some effects, but also the voltage adjustment. We see, I have showed you that we can adjust the voltage in the 110 kilovolt grid up to 500 volt, but they can manage with their step transformers to hold their voltage in a certain voltage band.
Thanks a lot. And then I have another question for you. It's coming from Suzanne Pato from the Regulatory Assistance Project. She's asking, what share of the DSOs in your territory participate in this scheme? Do they have any incentive to do so? And the reactive power providers, not fully sure what the last bit refers to, but yeah, so who or how many of the DSOs in your territory? You mentioned E.ON, but how many others participate and what's their reason for doing so?
Okay, between the transmission system operator and the distribution system operation, there is a law for collaboration. And with our grid customers, with the power plant, with the renewable power plants, the short answer is money, of course. And the federal government recognized that we shut down our power plants, conventional power plants, and therefore in the future, we think in the next 2-3 months, we get a market for reactive power. And here all participants and grid customers can make a bid for reactive power. This is the answer from the federal government in Germany.
Thank you. And we have another question that just came in from Ricardo, who earlier asked about the scientific overview of the project. He is now asking, was an estimate of avoided capital and potentially operating costs of TSO/DSO equipment for reactive power compensation and voltage control carried out before deciding on implementing the Amprion E.ON DSO cooperation agreement? So yeah, which costs did you look at beforehand in terms of capital and operating costs?
Yes, we have made a financial analysis about this, but the point is money cannot hold our grid stable. So the way of the exchange between distribution system operator and transmission system operator is the last call for reactive power provision. This is the last possibility for save our grid for voltage band violations. So there's more. The point is not the money. The point is more the grid stability.
Yeah. Okay. Thank you. And we have a very quick question from Miguel Olmedo, and he's saying, sorry if that has been said already, but is the project still at a theoretical experimental phase, or have you already started implementing it in practice, Marcel?
Can you repeat your question? Sorry.
So is the practice already in operation?
Yes, yes. The practice is in operation. I told you last year we used this concept 20 times in the west of Germany, in the county Rheinland-Pfalz, with our DSO.
Thank you. And then one more question for Marcel. What proportion of the 110 kV Amprion transmission is cabling versus overhead lines. Just wondering how the 110 kV infrastructure changes between nighttime and peak loading, in brackets, inductive and capacitive properties affecting the reactive power and voltage levels.
Yes, actually, we have, of course, more overhead lines in Germany, but we see that the cabling proportion rises, especially in the south of Germany, and therefore we think that we predict that we get more and more higher voltages in our grid.
Thanks a lot. The chat for now is quiet, so I take the opportunity to ask a couple of questions. I'd be interested in also like bringing the two approaches that both of you shared together a bit closer. And I mean, you're basically pursuing very similar goals with what you're doing, but have decided on slightly different paths of achieving these similar goals. So I'm not a technical expert, so I get to ask potentially stupid questions. But are these two approaches something that you could layer on top of each other and then further increase the capacity and the flexibility when it comes to integrating renewables? So Emma, would it be interesting to do what Amprion does on top of what you're doing? Are you maybe already doing something similar? And then the other way around, same question.
Sure, yeah. So as synchronous generation disappears, so Marcel had the diagram with the conventional plant disappearing. You know, we lose inertia, which was our problem, but we also lose reactive power support. So yeah, we've been also looking at how we can avail of reactive power from wind farms at the distribution level in Ireland and Northern Ireland. And we have a couple of pilot projects that are under consideration at the moment. There's a lot of technical challenges around them, as communications was mentioned as well earlier. So and then, you know, set points and the interaction between the TSO and the DSO. So yeah, we would love to be able to avail of the reactive power support from wind farms at the distribution level, and it's a matter of incentivizing them to do so, making sure that everyone is paid for providing that as well, and getting it when we need it reliably as well. So a lot of technical challenges to bring that forward, but we are looking at that now. With the advent though of synchronous condensers, they are also providing reactive support, the low carbon solutions. So that is another source of reactive power for us.
Thanks a lot. And Marcel, same question for you. Are you fishing in similar waters as EirGrid and SONI have? Are you thinking about similar approaches?
Yeah, I'm not an expert for frequency like Emma, but at Amprion we have a department, I think 5 or 10 people, which are looking only on frequency and RoCoF events. So this is a big and important issue at Amprion.
Thanks a lot. And both of you have mentioned collaboration as an important aspect in developing the approaches that you've presented here today. You've specifically always highlighted the importance of the collaboration and the quality of the collaboration with the DSOs that you've worked with respectively. Can you maybe talk a bit more about the importance of collaboration projects in your work overall, and for the energy transition overall? So why is it so crucial, or why is collaboration so crucial in the context of your projects and also beyond the projects that you've talked about us here today? And are there maybe any, like, you always hear that inspiration and solutions can come from unlikely places. So are you also looking beyond technical or beyond the DSOs when it comes to technical collaboration partners, maybe, I don't know, think tanks, lab projects that are happening at universities or at startups maybe? So is there anything exciting in terms of technical collaboration coming up that would maybe surprise the audience here? So is there something you can tease, or alternatively, maybe talk a bit more about the collaboration and the need for that specifically in the projects that you presented here today?
Sure, Stephanie. Yeah, so I mentioned our new program is the Shaping Our Electricity Future program, and we have a fourth pillar on that now, which is solely called engagement. So that's engaging on all aspects of, you know, increasing building out the transmission grid along with all of the other things that we're doing. So we definitely put a focus in on that. And we have our advisory council for the SOEF as well. So we've taken the same model as the DS3 advisory council, again with quarterly meetings, trying to learn from industry. You know, the industry is so big now, there's so many different players and everybody is doing amazing things. And we need to learn from each other and understand each other's strengths and weaknesses to, I think, everyone look forward to towards the 2030 goals and beyond to 2050 net zero as well. We do sponsor some PhD projects as well in EirGrid and SONI, and yeah, lots of other things going on as well. So maybe Marcel, if you guys got something similar.
Yes, I think the major key is communication of all and collaboration, but we need digitalization and better technical communication. This is a key for our projects, and also on the one hand we can install new compensation units, but on the other hand we can use or communicate with each other and maybe avoid to build new power plants. And this is the idea of the collaboration. This is only possible with new communications concepts and digitalization in our energy structure.
And who are you working on for that, or who would you be looking to? So is this strictly something that you work on between the TSO and the DSO, or are there other collaboration partners that are involved in this?
Yeah, of course, we have our grid customers and of course distribution system operators. Yeah.
Okay, thanks a lot. We have some more specific questions again that have popped up in the chat in the meantime. The first one is for Emma. It comes from Mike Hogan from RAP. So do you have plans to extend the tolerance for RoCoF even further? Apologies if you already addressed this.
Yeah, for the moment we're sticking with the 1 hertz per second, and we're confident that will get us to 2030 anyway.
Great, thank you. Very quick answer. And then we have one more for Marcel. And it starts with an apology. Sorry, I'm not an expert. This comes from Jan van der Putte from Greenpeace. What are the opportunities for wind farm operators for generating income, not only to participate in the energy markets, but also in supplying grid services by supplying reactive power and reserve capacity? What are the requirements for digitalization / SSI platforms, and are there any obstacles?
Yes, the major business for wind parks is the provision of real power, of course. But with the reactive power market, there's a new business, a new market. And this is a new, they can earn money by provision of reactive power. And this is a big benefit for wind farm operators. And this is supported by our federal government in a big market, which is used, we hope, in the next 2 or 3 months. But yes, you have the right ideas about the requirements for digitalization. We cannot make a phone call to the wind park customers. So it is necessary to build up a digitalization, a communication infrastructure to the wind park. Yes.
Mm-hmm. And how far has that come? Building that digital?
Yeah, actually, the companies which build the wind parks have this requirements and have the possibility, but actually the communication infrastructure to us, to the TSO, is missing. So we have to enhance our communication grid in the future.
Okay, so that's the obstacle right there. That still needs to be built. We are close to the end of this webinar. So if you still have any questions, make sure to post them in the next couple of minutes. But I want to piggyback a bit on the obstacles question. And just want to ask both of you, I know you both talked about this a bit when you addressed the testing phases of your projects. But can you talk a bit more about difficulties in the development process of your practices? So were there any really difficult aspects that you had to overcome? And do you see any benefits in learning from failure? I've especially experienced when like talking to people in the US, that there's a very different mindset to us in Europe when it comes to learning from failure, and a lot of openness in talking about things that didn't work and what came out of that in terms of like light bulb moments. So did you have any of those? I think, Emma, you mentioned a few false starts in your presentation. So what did this lead to in terms of improvement? Yeah,
I guess even prior to that, we had a lot of difficulties in convincing the thermal synchronous generators that their plant would be able to withstand the higher levels of RoCoF. And everybody knew it was going to be a hard slog to get that evidence collated. So we worked with the regulatory authorities here in Ireland, on Northern Ireland, and they came up with a incentive payment mechanism to encourage the generators to carry out the studies. And there was early delivery incentives as well for that. So that worked out well in the end. But it did take a number of years. Like, it took nearly 6 years between getting the approval in principle for the grid code and getting the final generator signed off in order to start the trial. So there was a lot of reporting needed over that period too. So it was quite challenging. And then, as I mentioned, at the DSO levels, the sheer volume of units that needed to have their settings changed was absolutely phenomenal. Like, I don't know how they did it. Managing 800 customers to get all those settings changed is phenomenal, and we all realized how important it was. So I think that end goal was the driving factor behind it. So I guess a lot of learnings about what you mentioned earlier about the collaboration and bringing people on the journey with you as well, and making sure they understand what the end goal is and why it's important.
Do you think there would be any benefit in a bit of a cultural change in terms of being a little less risk averse and like testing more things also in operation early? I realized that it's a very sensitive business, electricity transmission and distribution. Do you think we're daring enough in testing new approaches, and could we make bigger leaps if we were more daring? Or is this too sensitive a business to do something
No,
like
I
this?
think like when I was reflecting back on the project and putting myself back into, you know, somebody's eyes 15 years ago, you know, the person who said, yes, we can hit 75% of, you know, our demand can come from non-synchronous sources. Like I don't think I would have believed it back then. Somebody had that belief and they, you know, created the DS3 program because it needed a structure, it needed a framework, it needed support from many areas. So yeah, so somebody had that belief, and fair play to them, because none of this would have happened without that. Yeah. And I think, yeah, for the future, you know, when we say, you know, 3 units, 3 synchronous units on the island of Ireland, Marcel has alluded to having, you know, 0 in Germany. So that is pretty ambitious, and why not? Let's give it a go. Let's see what we can do.
Thanks a lot. Marcel, do you have anything to add to this?
Yeah, in Germany, we had the idea of the project is not new, because we had the idea 10 years ago. But the problems of our project was that we cannot win grid customers for our project. And now we have the support of the government with the reactive power market. And now we can win some grid customers to participate at our project. I have to tell you, this is not a project anymore. This is a real, this is our daily business. And this was a problem at the end, at the first time. Yeah.
All right, thanks a lot. I'm seeing one last question. I know you're not too late, so we have Marco Merlo, who's the last question I'm going to take. Could I ask a feedback on how, in your opinion, tools TSOs and DSOs are using to estimate the needs of the grids are mature, i.e., how much consolidated is the evaluation of the needs, real-time evaluation, or ex ante?
Yeah. The need for the need for real time is very good, because we see the need by looking on the voltage in our grid, so we can approximate the need directly. This is no problem. But ex ante, there are some problems. Of course, we make some predictions, but every prediction has some failures, and so we only can approximate the demand, the need for the future.
Mm-hmm. So Marco is clarifying, I mean, needs for reactive power. This is what you've been answering, right?
Yeah. Yes.
Yeah. Okay, great. Good.
Yeah, we've just launched a new tool as well in our control room, the voltage trajectory tool, that enables grid controllers to assess the impact of varying sources of reactive power coming from across the system. So that's another innovative tool that we have alongside our look ahead tool as well.
Great, thank you so much. And thanks a lot to everyone who joined us today. Thanks a lot, especially to Emma and Marcel for your very interesting presentations. I'm gonna close this here. Yeah, just again say thank you to all of you. Yeah, and encourage you to keep sharing best practices that you encounter, similar to the ones we talked about today or in very other realms. Yeah, we're always excited to hear about them, to keep sharing them with our network. We hope that webinars such as this and other events that we do tailored around best practices also lead to all of you who are here today getting to know each other a bit, and maybe connecting also outside of these occasions. So yeah, just keep talking to each other, keep developing great practices, and I'm excited to talk to you again soon in another installment of a best practice webinar or on a different occasion. And yeah, thanks again to our presenters and all of you who joined us today, and have a great afternoon. Bye-bye, everyone.
Bye.
Thanks, Marcel. Bye.